The last section in this chapter we are covering is percent yield. You will be able to, given the actual quantity of product, determine the percent yield of the reaction. In our problems up to now, we assume that all of the reactants completely changed into product. Thus, we have calculated the amount of product as the maximum quantity possible, or 100%. While this would be an ideal situation, it does not usually happen. As we carry out a reaction and transfer products from one container to another, some product is usually lost, and this is in real life. In the lab, as well as commercially, the starting materials may not be completely pure, and side reactions may use some of the reactants to give unwanted products. So 100% of the desired product is not actually obtained. Here's some terms you need to know. Our theoretical yield is the amount of product we expect if all the reactants are converted to the desired product. Theoretical yield is mathematically. Actual yield is the amount of product that is actually obtained when the reaction takes place. And the percent yield is taking how much we actually got and divided by how much we theoretically should get on paper and times it by 100%. On a space shuttle, the lithium hydroxide in the canisters removes carbon dioxide from the air. Here's our problem. Lithium hydroxide plus carbon dioxide gives us LiHCO3. What is the percent yield of LiHCO3 for the reaction of 50 grams of lithium hydroxide gives 72.8 grams of LiHCO3. So this is telling me how much I actually got. I'm just going to put an A. We need to figure out theoretically how much LiHCO3 we should get if we start with 50 grams of this reactant. Let's do the math. The first step is taking that 50 grams of lithium hydroxide, finding the molar mass of it, and going from grams to moles. This is our first step. Once I know how many moles of lithium hydroxide I have, I can go from moles of reactant to moles of product. Notice that it's a 1-to-1 ratio. So I'm going to have my moles of LiOH on the bottom to moles of LiHCO3, and then finally we need to find the molar mass of our product, which should be about 67.96 grams. Now we need to multiply across and divide going down, and we should get 142 grams of LiHCO3. So this is how much we theoretically should get on paper. We're told that we actually got 72.8 grams. So we take our actual and divide it by our theoretical and times it by 100. Let's plug that in. 72.8 grams divided by 142 times it by 100, and we should get 51.3% yield. See if you got the same thing. Take a minute to look at the learning goal and see if you understand it. There is also plenty of practice problems in your textbook, and we will go over a few more practice problems right now. Let's do some sample problems. Pause the video here and calculate the total mass of the reactants and the products for each of the following, A and B. You do it first, and then you can check our answer. Let's check your answer. For letter A, I did 4 times 1 potassium plus 2 oxygens, which is 32. And on the left side, I got 188.40 grams. On the right side, I took 2 times, and then I added up 2 potassiums and 1 oxygen to get 94.2. And on the right side, I got 188.40 grams. Letter B, I did 6 times 1H plus 1 Cl to give me 36.458 plus 2 aluminums, so 2 times 26.98, and on the right side 3 times H2s plus 2 times AlCl3, and 1 aluminum and 3 chlorines would equal 133.33. Add up the left and add up the right, and we should get 272.71 grams. For this next problem, you're going to use this chemical reaction, and you're going to calculate the moles of iron needed to react with 2.75 moles of sulfur, and figure out how many moles of iron 3 sulfide is produced when we start with 0.758 moles of sulfur. Pause the video. Let's look at our final product. If I started with 2.75 moles of sulfur, I'm already at moles, so I can go right to my mole-to-mole ratio. And it wants to know how many moles of iron are needed to react with that sulfur. So I'm going from sulfur to iron, which is 3 moles of sulfur for 2 moles of iron. Should get 3 significant figures, 1.83 moles of iron. The next one is 0.758 moles of sulfur. So we're starting with moles of sulfur again, but we want to go to product, our iron 3 sulfide. So our mole to mole ratio here is 3 moles of sulfur for 1 mole of our product. And we should get 0.253 moles of our product. Pause the video here to try this next sample problem. Let's see how you did. I started with 0.756 moles of water, and I want to know moles of oxygen. So I just had to do my mole to mole ratio. There's 4 moles of H2O for every 5 moles of oxygen. So 0.756 times 5 divided by 4 should give me 0.945 moles of oxygen. My next one, I'm starting with 0.243 moles of propane. I want moles of oxygen, so I just have to look at my mole to mole ratio of propane, 1 mole of propane for every 5 moles of oxygen to get 1.22 moles of oxygen. Pause the video here as you try to work through these problems. All right, for part A, we want to get to grams of CO2, and we're starting with grams of oxygen. So let's look at our path that we're going to take. We've got grams of oxygen. We need to get to moles of oxygen. That's from here. And then we need to compare moles of oxygen to moles of CO2 using that mole to mole ratio. And it wants grams. So then we go from moles of CO2 to grams of CO2. This is using molar mass. This is using molar mass. And this in-between part is using that mole to mole ratio. Let's get started. There's 2 oxygens, so that would be 32 grams of oxygen and 1 mole of oxygen. Then we just said that there's 5 moles of oxygen for every 4 moles of CO2, and for every 1 mole of CO2, there's about 44 grams of CO2. Let's make sure that everything matches up diagonally. Grams of oxygen and grams of oxygen will cancel. Moles and moles of oxygen will cancel. Moles of CO2 will cancel. Let's multiply across and divide by whatever 32 times 5 is, and we should get 27.5 grams of CO2. Let's look at the next problem. We're given grams of water. We want to get to grams of C2H2. So we've got grams of water. We got to get to moles of water. Then we need to compare moles of water to moles of C2H2. It's a 2 to 2 ratio. And then moles to grams. Let's get started. We need grams of H2O for every 1 mole of H2O. That's its molar mass. 16 plus 2 is 18.015. We just said that there was 2 moles of water for every 2 moles of C2H2, and for every 1 mole of C2H2 is about 26 grams. And if we multiply across and divide going down, we should get 93.9 grams of C2H2. Check your work and see how you did. Take a minute using this equation to solve these 2 problems, calculating the mass in grams. Let's get started. Letter A wants the grams of C7H16 that's needed to produce 15 grams of water. So we are taking what we're given, and that's our starting point, 15.0 grams of H2O. We need to develop a plan to get from grams of water to grams of C7H6. So if we've got grams, we need to get to moles using the molar mass. Then we need to do our mole to mole ratio. 8 moles of water to 1 mole of C7H16, and then go from moles to grams. Let's get started. We want to know how many grams of H2O there are in 1 mole of H2O, which should be about 18.015 grams. That's water. Make sure you label. And we just said that there was 8 moles of water for 1 mole of C7H16. And then our last step is going from moles to grams. And the molar mass for that is 100.2 grams. If we multiply across and divide going down, we should get 10.4 grams of C7H16. For part B, we're given grams of C7H16. We want to get to grams of CO2. So we're going from here to here. We just found the molar mass of C7H16, which is 100.2 grams. There is a 1 mole of that to 7 moles of CO2. And then the molar mass of CO2, we would say for 1 mole of CO2 is 44 grams of CO2. Plug and chug, and we should get 76.9 grams of CO2. That should be our answer. Pause here to try these limiting reactant problems. It wants to know if I'm starting with 4 moles of CO and 4 moles of H2, so those are both of my starting points down here. What's the limiting reactant? How many moles of methanol can be produced? Well, let's figure out how many moles of methanol can be produced from both of these. Let's go from CO to CH4O. It's a 1-to-1 ratio. Therefore, we can make 4 moles of CH4O. Let's look at H2. There's 2 moles of H2 for every 1 mole of methanol. So that means 4 times 1 divided by 2 would give me 2 moles of CH4O. So can I make 4 moles or can I make 2 moles? I can only make 2 moles. I only have enough hydrogen to make 2 moles. I don't have enough hydrogen to make 4 moles. Sure, I've got enough carbon monoxide, but that just means I'm going to use up all of my hydrogen to produce 2 moles, and I will have excess of CO. The second problem says that I have 1.50 moles of CO and 6 moles of H2. So again, I have to have 2 different setups here, and we want to know again the limiting reactant and how many moles of methanol can be produced. So in both of these, again, I would have the same ratio, 1 mole of CO to 1 mole of CH4O. So that would make 1.50 moles of methanol. And down here, I have 2 moles of H2 for every 1 mole of CH4O. 6 times 1 divided by 2 is 3 moles of CH4O. So can I make 1.5 or 3? In this case, I can only make 1.5 moles of methanol, and so my limiting reactant is the carbon monoxide. We're going one step further now and finding the mass of the product from a limiting reactant. Last one we just stopped at moles. Now we're going to mass. Pause here. First, we want to find out how many grams of SO2 are formed. That's where we're going to end. We're going to end at grams of SO2. We are starting with 8.52 grams of H2S. So we're starting here with grams of H2S. If we start with grams, hopefully it's ingrained in your skull to get to moles using the molar mass. Then I need to jump from moles to moles and then go from moles to grams because it wants grams. Let's start right off with finding our molar mass of H2S. I got 34.09. Then we look at our mole to mole ratio, and it's a 2-to-2 ratio. And then we need to go from moles of SO2 to grams of SO2. And we always find the molar mass for 1 mole of a substance. And adding up 2 oxygens and 1 sulfur, I got 64.07 grams. Plug and chug, and we should get 16.01 grams of SO2. Now let's move on to the second part of the question. We have 9.60 grams of oxygen. We want to figure out how many grams of SO2 are formed. So we're going to start with grams of oxygen, go grams to moles using the molar mass. There are 3 moles of O2 for every 2 moles of SO2. And then we have the same molar mass, the last piece here. And if we plug and chug correctly, we should get 12.8 grams of SO2 for the second part of part A. So answer the question. Can we make 16.1 grams of SO2 or 12.8 grams of SO2? Well, we can only make the smaller number. Our limiting reactant here would be oxygen. It didn't ask for it, but we can only make 12.8 grams, not the 16. Let's look at part B. It wants to know how many grams of water are formed. We're given grams of H2S and grams of O2. So here's my grams of H2S and grams of O2. We need to have 2 separate problems. If I have grams of anything, I have to get to moles. Here's my molar mass for H2S. There's my molar mass for 2 oxygens. The next step is my mole to mole ratio. I have to look at my mole ratio for H2S, which is 2, compared to water's 2. So it's a 2-to-2 ratio. And finally, I have to look at my molar mass of water. I got 7.93 grams of water would be produced from 15 grams of H2S. Oxygen, we already did the molar mass. The mole ratio is 3 moles of oxygen for 2 moles of water. That's the ratio from the balanced equation. And then the last part is the same as this last part of the first one, the molar mass of water. And I got 9.38 grams. So how much water can be produced from this much H2S and this much O2? Can we produce 7.93 or 9.38 grams? It's got to be this one. 7.93 is the smaller number. That's how much water will be produced. So our limiting reactant would be H2S. This is our last set of problems. Pause here to try to figure out the percent yield. All right, let's see how you did. I started with 8 grams of CO2, but we want to know the percent yield of this product, LiHCO3, and we're told that it produces 10.5 grams of LiHCO3. That is my actual that's been produced. We need to figure out how many grams of LiHCO3 would theoretically be produced from 8 grams of CO2. So this is my starting point. And if I have grams of CO2, I need to go to moles of CO2 using the molar mass. I need to look at my mole to mole ratio of CO2 to product. And then I need to look at the molar mass of that product. If you plug and chug, I got theoretically, and I'm going to put a T here for theoretically, 12.35 grams. That's how much I theoretically should produce. Here's how much I actually produced. So we do actual divided by theoretical, 10.5 grams, divided by 12.35 grams, and we should get about 85.0%. For part B, we want to find the percent yield again of our product. This time we're starting with 35 grams of lithium hydroxide, so that's my starting point. And we're told that it produces 76.6 grams of product. That's my actual again. I took my 35 grams of lithium hydroxide, I went grams to moles, I added up 1 lithium, 1 oxygen, 1 hydrogen. It's a 1-to-1 ratio again, and it's the same molar mass for the same product. I got 99.32 grams. Again, we're going to take our actual divided by our theoretical, and I got 77.1% yield. All right, that's it for our practice problems, and that's it for Chapter 9.